In the last series of videos in this playlist, we looked at shear stresses, which occurs when a force causes surfaces and layers in the structural element to slide away from each other. Depending on the direction that force is applied to the element, it can also cause that element to rotate or bend. When this occurs, a reaction is induced in the structural element that opposes this bending force. This reaction is called a bending moment. We see examples of bending in applications like aeroplane wings, when the upward force on the wings due to air rushing over them causes them to bend upwards during flight. We also see bending in static applications, such as beams and columns. In this video, we will analyze bending in beams in simple structural applications to gain a basic understanding of bending moments. Such analysis is useful in understanding and visualizing where bending stress occurs in a structure and can thus help us design structures that don't fail under their intended load. Let's start our discussion on bending moments with a quick review of the concept of torque, which is the rotational equivalent of a linear force. It is the ability for a force to cause an element to rotate. Consider a simple beam that's connected to a brick wall by a hinged joint that can allow the beam to rotate about that joint. If we now apply a force to the right end of the beam in the direction that is perpendicular to the length of the beam, that is, the force is directed at an angle of 90 degrees to the length of the beam, then the force will cause the beam to rotate as shown. The strength of the rotation is dependent on three variables: the magnitude of the force, the distance from the force to the point of pivot, or the lever distance, and the angle between the force and the length vector. The formula is given by tau being equal to the product of the force, distance, and the cosine of the angle. Torque has a unit of Newton meters. When the angle between the force and the length vector is 90 degrees, then the formula for torque simplifies to just being force multiplied by distance. Thus, the greater the force is applied perpendicular to the beam, the more torque there is on the beam. Conversely, the further the perpendicular force is applied from the point of rotation, the greater the torque. Now consider that our beam is fixed to the wall and it's not free to rotate. If we now apply the same force to the end of the beam, that force will no longer cause the beam to rotate. Instead, it causes the beam to want to bend. If the beam is not stiff enough to resist the bend, the beam will distort and the end of the beam will deflect. The beam will continue to bend until it reaches its maximum deflection. At this point, the beam will stop bending and is said to be in equilibrium. This means that the net force on the beam is equal to zero. Therefore, there must be an opposing force to the load that points in the opposite direction to the load. This force is called the shear force and is created by the beam to react against the external load and stops the beam from bending any further. This bending reaction is what is called a bending moment. So while the load creates a bend on the beam in a clockwise direction, the shear force opposes this bend in the anti-clockwise direction. Bending moment is defined in the same way as torque, that is, it is the product of the force and the perpendicular distance from the force to the fixed point which the beam will bend from. Thus, the greater the force that is applied perpendicular to the beam, the more bending moment there is in the beam. Conversely, the further the perpendicular distance is from the point of the bend, the greater the bending moment. So bending moment is the static equivalent to torque. While torque causes the element to rotate about a point of pivot, bending moment causes that element to bend about that point. Bending moment also has the unit of Newton meters. Now let's have a look at an example where a beam is fixed at two locations, namely at its ends, and we apply a load at its center. We can see that as we add load to the beam bend takes the shape of a concave that looks like a smile. At this point, it's worth discussing the sign conventions. Just like when we looked at shear forces, we defined the upward shear to be negative and the downward shear to be positive. We also need to define the positive and negative direction for bending moments. When the bend is an upward concave and looks like a smile, this is called a positive moment. This occurs when the force is applied in the downward direction. But when the force is applied in the upward direction, it causes a downward bend that looks like a frown. This is called a negative bending moment. One useful way to remember them is as emojis. Smiley mouth is positive and a frowning mouth is negative. The last characteristic of bending to consider is what happens to the materials that make up the elements during the bending. From the video on shear, we saw that an applied load can cause the vertical layers to slide from each other and the materials to induce a vertical shear force to oppose it. But there's also shearing that occurs along the length of the beam as well. As the external force pushes down on the beam, the top layer of the beam are pushed closer together and are compressed. So the top layers experience compression forces. The bottom layers, on the other hand, are stretched and the layers are pulled away from each other. So the bottom layers experience tension force. The layer at the center of the beam experiences no horizontal shear forces. If we look at the horizontal forces at the left end of the beam, the normal convention for beam analysis is that we start at the left end. We see that the top of the beam experiences compression forces to the right and the bottom end of the beam experiences compression forces to the left. The two shear forces act to rotate the left end of the beam in a clockwise direction. This clockwise direction is taken to be positive in the normal sign convention for beam analysis. If the applied force was reversed, then compression would occur in the bottom layers of the beam and tension would occur in the top layers of the beam. In this case, the left end of the beam would experience a rotation in the anti-clockwise direction, which is taken to be negative bending. Now that we've got the basics of bending moments out of the way, let's look at analyzing bending moments in the next video. In summary, a bending moment occurs when a force is applied to a fixed element to cause it to bend. The bending moment is the element's reaction to this bend. The magnitude of the bending moment is equal to the product of the force that is applied perpendicular to the distance from the force to the point of reaction. Bending moment has a symbol capital M and has a unit of Newton meters. When the bend creates an upward curve, it is called a positive bending moment, and when the bend creates a downward curve, it is called a negative bending moment.